Well, hi everybody. It is my pleasure today to introduce our speaker, Stephanie Juneau. Stephanie did her undergraduate work in Montreal and then did a master's degree in Victoria, Canada. She then went to Arizona to graduate school. We actually met there when I was a postdoc at the National Optical Astronomy Observatory, and she was doing her PhD with Mark Dickinson. She was at the University of Arizona, and he was working where I worked, and people collaborated across the street there. Afterwards, she went to CEA-Saclay outside of Paris for a Marie Curie fellowship. And after being there for 1 year, she got a staff position at CEA-Saclay. Recently, she's moved back for a short-term appointment at the National Observatory in Tucson, working on the NOAO data labs, trying to work simultaneously on bringing very large data sets to the masses in a very highly digestible format as part of NOAO's new initiatives, and also working on black holes and emission line ratios, which you'll hear about tomorrow, and about the supermassive black holes we'll hear about today. She's here tomorrow morning as well, so if you didn't get a chance to talk to her today, you can definitely email Kim and get on a time slot for talking to her tomorrow morning before her Astro seminar. It's really a wonderful pleasure to have her here today, and I'm looking forward to her talk. So.
Thank you, Greg. All right. All right. Hi, everyone. So it's a very pleasure to be here today. First time in Kansas, so this is all great. So I will be telling you about what I called it cosmic hide and seek, and you'll see why in the talk. But basically, I'll be telling you about supermassive black holes in the context of galaxy evolution and the connection between black holes and galaxies. So here's a short outline. So first, I will introduce the context. So as I was saying, the galaxy evolution context, but also I'll start with some basics review. So what are supermassive black holes? What do we know about them? What don't we know about them that we're trying to learn? And then I will introduce you some methods for identifying the active black hole. So what does it mean when a black hole is active? It means that there's new material right now being accreted onto the black hole, and this material is very shiny, so it makes a lot of activity. That's why we say it's an active black hole. And then I will talk about three aspects of black holes through the universe as the universe evolves. So the growth of black holes, the obscuration of black holes, so where in a case where we cannot see them, even though they might be active, so they would normally be shiny, but we still don't see them. And then lastly, because of all this energy with accretion around black holes, if this energy is released in the forms of winds or feedback, what all of these things imply, and how are they all linked in connection to galaxies. Okay, so let's get started. So first, the broad context. So what do I mean by galaxy evolution context? So in the current picture that we have of the universe, there was a Big Bang followed by dark ages, and then the formation of the first structures, so first stars, first galaxies. And as the universe evolves and the universe is expanding, at the same time the structures continue to develop and form and grow until we get this kind of zoo of galaxies that we see today. So galaxies of various shapes, various colors and sizes, and so on. So when we say evolution, it means that there's a change in galaxies with time. And what I want to tie into this picture is also what happens to the black holes across this time. So of course, in astrophysics, it's very convenient because all we have to do to reconstruct the history is just to look further and further away. And this is because it takes time for light to travel to us. So the further away we look, then the more we can see galaxies back in the past. So we can, this way, look at galaxies from far away, closer in to closer and closer in, so we can reconstruct how the evolution happens across cosmic time. OK, so now on to supermassive black holes. So the first thing I want to say about supermassive black holes is that they exist. Everybody got that? OK. Because it was a claim about black holes not existing. But those are astrophysical black holes.
I don't know if I'll buy it.
OK, let's see. Challenge accepted. OK, so the astrophysical black holes, of course, we don't know their shape in detail inside the event horizon. But what we do know about them, because we can measure it, is that they have a mass, and that this mass is enclosed within some volume. So in a sense, they're real because there's real mass there, and we can see the gravitational influence of this mass. So what do I mean by supermassive black holes? Supermassive means in the range of about million to billion times the mass of the sun. So that's a lot of mass to be in one astrophysical object. For example, the black hole at the center of our own galaxy, the Milky Way, is about 4 million times the mass of the sun. And when we say a size of the black hole, what we're referring to normally is the event horizon. So the event horizon is the surface around the black hole where gravity is so strong, or in general relativity, the space is so curved that we don't see any light escaping from that event horizon. So we cannot see anything that's inside the black hole. So this is, for a non-rotating black hole, this corresponds to the Schwarzschild radius. And to give you an example of numbers for these very massive black holes, so from 1 million to 1 billion solar masses, it would be between 3 million to 3 billion kilometers, which is in fact quite small given the mass of these black holes. So for the Milky Way black hole, about of the order of 10 or 13 million kilometers would be the size of this event horizon. And if we remind ourselves about the solar system, it means that this 4 million times the mass of the sun is well within even the Mercury orbit around the sun. So it's all this mass, 4 million times the sun, in this kind of tiny volume. And how do we know this? So for the black hole in the center of the Milky Way, we actually have had a very good way of measuring its mass because we're able to measure individual stars around the black hole. And if we follow the stars over a long enough time, we can see their actual orbit around the black hole. So this should be an animation here. So this is, well, of course, the stars are not necessarily purple. They would be very nice if they were purple. But this shows the actual positions, though, of the stars that were measured. And when I start playing it, you will see their orbit. They were observed in the course of 16 years and going. So I don't know if you can see. Now we can see the actual orbits of the stars. So basically, all these stars have elliptical orbit. So then if you have enough observation points with enough orbits, you can actually solve for the enclosed mass. And this is how we get the order of 4 million times the mass of the sun. And we know that we cannot see anything there. There's no object that's emitting light in the optical or infrared. But we know that the mass has to be in a small volume because the stars are going around something and they're not colliding with the thing. So there's a black hole right there. This is the Sag-A star, the center of our galaxy. So the next thing I want to say is that, OK, it seems that our galaxy has a giant black hole in the middle, but many other galaxies also have a black hole in their center. And what is very interesting and what makes us think that there's a connection between galaxies and their black holes is that if we measure the black hole mass and we measure the galaxy properties, such as the galaxy mass or the bulge mass inside the galaxy, these things correlate. So here, this is, I should use a pointer, I guess. What you have on the left-hand side is the black hole mass on the vertical axis against the mass of the central bulge. So these kind of yellow stars that's made on the drawing here. And it's basically a correlation. So this is actual data here on the right-hand side. And so you have, again, the black hole mass on the vertical axis as a function of the velocity dispersion of the stars on the bulge. So how the stars in the bulge of the galaxies are moving. And you can see that, in fact, this correlation holds over several orders of magnitude, and it's quite tight. So why is the black hole mass somehow proportional to the galaxy mass? How do they know about each other? Is it because they grow together? Is it because somehow the black hole influences the growth of the galaxy? Is it the opposite, that the galaxy somehow influences the growth of the black hole? Maybe when galaxies use all the gas from stars, there's nothing left for the black hole. So these are questions that we're right now still trying to answer. But it means that there's at least some clear hint that there must be some link between black holes and galaxies. OK, so now I'm going to move on to how do we go about identifying and finding black holes, and in particular, ones where there's some kind of activity, meaning that right now there's some material infalling onto the black holes. So it turns out that there's quite a few choices that we have with methods all across the electromagnetic spectrum, and even now with gravitational waves, although I'm not going to talk about this. But in terms of electromagnetic light, we can have X-ray signatures that are emitted right close to the black hole, right above and below the accretion disk. We can also have optical light, and this is either from, because this disk around the black hole, when material is falling in, becomes very bright in the optical. So if we have the correct view, we can see a bright point source. It could be also in the mid-infrared. And I'll show you a diagram later to explain this better. But the idea is that infrared light is tracing basically heat. And around black holes, when they're active, there's so much energy that the dust, any dust around the black hole will become very, very hot. And the dust is so hot that it glows in the infrared, but it's hotter around the black hole than around all the stars in the galaxy. So it's in the infrared, and hotter means shorter infrared wavelengths. So we have ways to see these signatures with infrared telescopes of hot dots from active black holes. And then radio, this is actually radio observations, and these are radio lobes, so coming from jets, coming from the black hole into opposite direction. And these can be much larger than the scale of the galaxy, which you don't see on this image. Here you just see the radio emission from the AGN. So this means that we have all these different ways to try to find active black holes. And combining these different ways is a kind of a picture that emerged with the years, and mostly in the 90s, about how to reconcile and how to explain all these different flavors or these different ways of finding active black holes. So this is called the AGN unification model. And according to this model, there's a black hole in the center with a accretion disk that's seen on the edge here. And then the disk flares, and it becomes the structure, which is we often call a torus, which is basically thicker, and it's a mix of gas and dust. And there's so much material of that gas and dust in this flaring disk or in this torus that if we were to try to observe this black hole looking edge-on, so if we're observing in this direction, we don't actually see the accretion disk because the light of the accretion disk is absorbed or is obscured by this material. So in order to see this bright point source from the accretion disk, we actually have to be looking in the opening of this torus. And according to this picture, these little clouds that are located, basically they could be clouds all around, but the clouds that are located in the opening angle of the torus will see the light from the accretion disk. So they will be ionized. So this is all this material here. It's like we're shining this bright light on both sides of the disk. So the gas becomes all ionized. And because there's dust in this structure, this is the very hot dust I was referring to before. So this means that in this picture, we expect to see radio from radio jets, which I did not describe, but they will be coming either on one side or on both sides away from the black hole. Infrared we can get from this hot dust from the torus. X-rays are coming from right outside the accretion disk. And then this narrow line region is a technical term. They're basically ionized gas clouds with narrow emission lines. And these are coming from any gas that basically sees the light from the accretion disk. So we have all of these different ways, and I'll show you before how we use them with observations in order to find black holes in a sample of galaxies. So what I'm going to move on to now that we have ways to identify black holes is how can we learn about growth and obscuration of black holes. So just to go back to this picture, obscuration meaning that if this model is true, if this is a true representation of black holes and active black holes, it means that if randomly we're looking to the side, we don't see it in the optical, or even the X-rays might be blocked partially. But if we look any other angle that we see the opening, then we see them. And the infrared light, we should always see it because the infrared light can penetrate through the dust and go on the other side. So it means that in infrared, we should find all of the black holes with respect of the angle. But then in X-ray, we might not find them all, depending if we're lucky or not lucky with our line of sight that we're looking at black holes. OK. So in terms of host galaxies, I will show these key properties. So how do we, basically what do we measure a whole galaxy? So we can measure what we call the star formation rate. So this is the rate at which a galaxy is forming new stars. So this is only measured in solar masses per year. So how many new stars per year are being formed in a galaxy? And in particular, I would be interested in star-forming galaxies, meaning that these galaxies are right now forming new stars. They're not dead. There's new stars being born. And then the stellar mass is another important quantity. So this is the total mass in stars formed up to now in that galaxy. And then combining these two quantities, we have the specific star formation rate, which is simply the ratio of the star formation rate, so how many new stars per year, to the total mass in stars so far. So what do we know about the specific star formation rate in galaxies going back in time? So this figure shows the specific star formation rate against redshift. So the higher the redshift, the more we're going back in time. And if you just look at this gray band, it turns out that a lot of galaxies actually have a similar value of specific star formation rate, which we call sometimes a specific star formation rate sequence or a main sequence of galaxies. But it goes in the way that there's some spread, but it goes up when we go back in time. So in the past, galaxies were forming more stars per unit mass. They're forming less and less and less stars per unit mass now. So at redshift 0 is now. So galaxies live a lot along this sequence with some outliers that are boosted because they're forming extra stars, so they have a starburst, so they can be boosted up. And then if a galaxy stops forming stars for whatever reason, we say that the galaxy is quenching, so the star formation rate goes down, and then there could be some galaxies living down here, so they have a low star formation rate compared to their stellar mass.
Excuse me?
Yes.
How far back in time is 1.5?
So redshift 1 is about half the age of the universe, so this is like divided by 2.5. So maybe it's like 10 billion years ago. So the universe is about 14.
Is M star from the initial mass function of galaxies, or what?
So it's, yeah, it needs that, but it's integrated for the full galaxy. So it's the total mass in the form of stars integrated over the IMF, the initial mass function. So if I was able to put the whole galaxy on a scale in just the stars, what's the total mass? OK. So I wanted to show this because this is what I'm going to be using to look at where are galaxies and where are galaxies with a black hole compared to this sequence. So here are the actual samples. So this is work done from selecting galaxies in the infrared regime. So with either the Spitzer infrared telescope in space or Herschel, which is a more recent space telescope, so selecting at 100 micron, shown on the right-hand side, and then 70 micron was a Spitzer selection, which was a bit less sensitive. So this is a better, more modern and more sensitive instrument. So we have many more galaxies. So what you can see is the same plot of the specific star formation rate versus redshift, this time going out to redshift 1. And then the gray band is, again, what you expect, this kind of sequence of star-forming galaxies. And you can see that the black points, which are each galaxy from the sample, are on that sequence or above. And with the new, more sensitive instrument, we can detect fainter star formation rate. So we're able to have a more complete sampling of the sequence. And we even have some galaxies that are below the sequence. But all these galaxies here, we say that they're star forming because they have a non-zero star formation rate. Right now, they're forming new stars. So the question is, which of these galaxies are growing black holes right now? And are the galaxies growing black holes like spread evenly across, or is it more some kind of galaxies versus others? And there's another question also, which is, if the black hole is right now growing, is it obscured or unobscured? So in the unification model, this means that we see it from the side, that we don't actually see the middle, or we see it that we have a direct view. So if it's truly this random orientation effect that decides if a galaxy is obscured, if the black hole is obscured or unobscured, this should have nothing to do with the galaxy property, should have nothing to do with the specific star formation rate. So it should be randomly distributed here. So let's see what we find.
What explains the binning in the redshift? Doesn't it look like it's settling?
So these are fairly small field of view, so there might actually be some structure, cosmic variance. You mean here?
Right, yeah.
The redshift distribution will have a bunch of bulbs.
Yeah, so,
There's a stripe, there's a stripe.
okay. There's something in particular at this redshift of 0.8, just from the particular sample I'm using, because of the spectral range. I cannot measure the emission lines everywhere, and I cannot get a good redshift everywhere. In the sense that one sample, so at about 0.8, it starts being a little bit funny here with a sparser sampling above here. And then everything else, in terms of redshift, you have to basically imagine collapsing this. And there's a little bit of bumps and wiggles, but it's not so bad. It's not so...
Looks
There's
like
something at
1.6.
0.6.
Yeah.
There's something
Yeah,
at
the structure in the
0.5.
Yeah, there's real structure. So this is a small field of view. It's not the full, it's not a big field that we average over the structure.
In pencil-beam surveys, you always have these weird effects. It's called aliasing. It comes from just bringing things from the outside, from the edges of the thing inside, and they pretend to be where they're not really. And redshift effects also make these walls.
This is just voids and galaxies.
Yeah, in this case, this is real structure in this particular sample because we have small fields of view. So this is something called cosmic variance. So if I look there in the universe, I might see more galaxies at 0.6. But if I look there, I might see more galaxies at 0.4. And if I look there, I might see more galaxies at 0.5. So that's why we want the very big surveys, because then we average all this together and we get a more uniform distribution. But this is a small survey. It's not big enough to wash out all the structure. So there's some real structure in there. OK. All right, so what we did in terms of the approach here was to use this multiple wavelength information I introduced before. So we combine X-ray information, optical emission lines, which tell us about the ionized gas, and then infrared colors, which tell us about the hot dust, and then radio access, which tell us if there's these little radio jets. So we combine all of these ways together. And when we have all of this, we can say a couple of things. First of all, we can say if there's an active black hole according to any of these methods, so that's fine. But we can say more. We can say, is it obscured or unobscured? Because if it's obscured, the X-ray is going to be missing. It's going to be faint. But we're still going to see these emission lines from large distance. And we're still going to see the Arac colors. And we can still see radio. But the X-ray is going to be suppressed if there's a lot of material in the line of sight. So what I'm going to show you next is if I keep this plot of galaxies on a specific star formation rate versus redshift plane, and if I add where are the AGN, so the active nuclei, that are not obscured in the X-ray. So the X-ray are shining just fine. So they're here with these bigger symbols. So you can see that they're mostly on the sequence and a little bit below. So OK, fine. Other people have found similar results, so this is consistent. And then we can ask, where are the obscured or absorbed AGNs in the X-ray? So the X-rays are absorbed by intervening gas. But we can still pick out the AGN with other methods. And these are up there with these orange symbols. So you may already notice that there's a bit of a different trend. So the orange symbols tend to be also somewhat on the sequence, but going higher. So they have a higher specific star formation rate compared to the X-ray unobscured AGN. So that's funny, because we would not expect this from just this orientation model. Because orientation would not, of this accretion disk and this torus, would know nothing about the host galaxy. So this means that the picture is a bit more complicated. We have to see how somehow the obscuration of the black hole in the middle of the galaxy knows about what the galaxy is doing on much larger scales. So we think that there's two possibilities. There are two possibilities. So either the host galaxy itself, because it has so much gas, and that's why it's able to form all these stars, all this gas gets in the way of the X-rays. Even though if it's not close to the black hole, it might just, anything along the line of sight basically will contribute to the absorption of X-rays. That's one possibility. And the other possibility that somehow the smaller scale torus, because it's made out of gas and dust, it needs, if there's more gas on the outskirt of the galaxy, then there's more gas on intermediate scale and more gas on small scales, and all these scales relate. So the gas will trickle down eventually, and the torus is somehow not independent from the galaxy. So we cannot distinguish right now between these possibilities, but it's very interesting to notice this difference between the obscured and unobscured active black holes on this plane here. All right, and now I'm going to show you a trend as a function of just the star formation rate in galaxies, which we measure from the infrared light, but this is not the super hot infrared from the hot dust, it's the cooler infrared from the stars. So what we have here is a measure of star formation rate indirectly. So more galaxies to the right, the more this galaxy is forming a lot of stars per year. And what I'm showing here in the red point is in these bins of star formation rate in the host galaxies, how many of these galaxies have a black hole that's accreting right now? Is the black hole accreting or not? This is what we call it, if it's active or inactive. But what's the fraction of accreting black holes? We can detect them. We know that they're active right now. As you can see, there's a trend of increasing fraction with star formation rate. So this means the more galaxies is forming stars actively, the more likely it has an active black hole. So somehow the black hole activity seems to know about the star formation rate of the galaxy. What does that mean? Well, the star formation rate, we think, is the most closely linked with the gas mass, because you need gas to form stars. So gas needs to cool and form stars. That's how you form the stars. Therefore, if you have more gas, you can form more stars. And also, you can fill your black hole. So in fact, this is actually quite logical in hindsight, that it's suggesting that there's just perhaps the same gas reservoir. So you have more gas, you can form more stars, and more of that gas also will go to the black hole, and you're more likely to be able to grow your black hole. So these points here are the results from the first study that we published in 2013 with the Spitzer sample. And when we just recently revised it with the more sensitive data, we actually find a very similar trend. So these are the two studies together. And we can extend it now, although with bigger error bars here, but we can extend it to even fainter galaxies with smaller specific star formation rate, and we seem to get a continuation of the same trend.
So is this over all redshifts or a specific redshift?
Yes, sorry, I should have emphasized. This is the sample I was showing you before, so it's mostly between redshift 0.3 and 1. Is this sample here. Right, so the takeaway points from this first part of the work is that the black hole growth seems to be linked to their galaxies, which could be surprising just because there's such different scales. But on the other side, it's not so surprising if we know that with gas we can make new stars, and with gas we can also grow black holes. And the second takeaway point is that the black hole obscuration also seems linked to galaxies. And this is more surprising because the most popular model so far was this unification model, where it has nothing to do with the galaxy, but just with what's going on just outside the black hole with this torus. But now it seems to be that there's a relationship with the specific star formation rate. So we have to revise how we think of black hole obscuration. So the next topic is actually this phenomenon of accretion onto black holes is very, very good at producing energy. There's a very good conversion of the mass being accreted into energy being released. And this energy can create winds or heat, and also perhaps cause some feedback because this heat is injected back into the galaxy. So what can we say about AGN feedback? So AGN meaning the active nucleus when the black hole is active. So first of all, there's plenty of energy there. The energy budget is no problem. In fact, there's enough energy with a highly accreting black hole that you could unbind the entire galaxy. This is not happening. We don't see galaxies falling apart, but there is a lot of energy there. And there's two different phenomena, and I'm mostly going to talk today about what comes out of the accretion disk. but it's also radio jets, which I've shown before. And I'll show you some other work, but I've not myself studied them too much so far. So what do we see? Well, overall, we see a lot of observations that have shown these winds coming out when there's an active black hole. So this figure here, this is work by Chris Tremonti et al., shows the velocity of winds coming out of galaxies as a function of how bright or massive the galaxy is. What is very interesting is, well, you can see here the range. So this is about 100 kilometer per second wind, and then 1,000 kilometer per second, and then this is really fast. This is 10,000 kilometer per second. So these things are quasars. So quasars meaning the most active, most energetic active black holes. So they can make really fast winds, like 10,000 kilometers per second. And this is a earlier sample, but you can see this trend. So there's also actually some of these winds are not from black holes, they're from stars. So these are starbursts, so meaning that they have a lot of stars forming at the same time, and stars make winds and supernova explodes, and that also makes winds. So you can have winds from starbursts as well, but as you can see, they're not quite as fast as the winds you get from black holes in general. So we know that winds exist, but we still don't know what's really the impact on galaxies because of that and because of these winds. So I'll show you a study from simulations to try to predict the impact of radiant feedback, and using two different types of feedback. So this is simulations of isolated galaxies. This is a disk galaxy shown here. So this is kind of trying to show you the 3D, but this is a galaxy with lots of gas. So it has this very clumpy structure, but this is a whole galaxy size, so about 20 kiloparsec, on the side. And the simulation is with AMR, which is adaptive mesh refinement, meaning that it's a fine mesh grid where there's a lot of gas, like in the dense clumps, and it's a bigger grid when the galaxy is more extended and diffuse material. And this allows us at the same time to have a simulation box big enough to have an entire galaxy, and yet have grid small enough to resolve what's going on in the fine structure of the gas in the galaxy. And especially we're interested when this gas gets close to the black hole, what's going on. So there's two forms of feedback. One is just thermal feedback. So when the black hole, which is located at the center here, gets mass and gets energy, some of it is redeposited as thermal energy, so as heat around the black hole. And this will actually, I'll show you the result of the simulation in a moment here, but you see that this will create this giant bubble and winds going away from the galaxy. And then the other feedback is from radiant photonization. So we know that there's a black hole in the middle there. So what we've been doing, this is work led by former PhD student Oriane Rost at CEA-Saclay. So she's been tracing all these different lines of propagation from the black hole in the galaxy in all different directions. And along each of these lines, she's saying, okay, this is like an active black hole, so I'm going to put a spectrum, an ionizing spectrum from the accretion disk from the black hole, and propagate with radiative transfer so that the light from the black hole through the medium of the galaxy, and see how far the gas is going to be heated or ionized. And this was done with a range of luminosity from the black hole. We can say it just has a moderate accretion and luminosity, or it's very bright, like a quasar, which is the most extreme luminous active black holes. So what do we find from this work? So the thermal feedback was implemented earlier, and this is work by Jared Gaber in 2013 and 14 papers. And this shows basically a simulated disk galaxies on the edge. So it's a disk galaxy, but it's seen on the side, right? So you just see it from the edge. So the scale bar here is 10 kiloparsec. So this is really like a full galaxy size. And then this is a map of the temperature of the gas. So where it's darker is because the gas is cooler. And as you expect, this galaxy, all the cold gas is in the disk. So it's fairly thin, though it's not super, super thin. But this is the disk of the galaxy in gas. And then this is gas that has been around the galaxy, more in the galaxy halo. So what's going on? I have a video that always crashes my presentation, so I'll show you some snapshots first. So this is what happens in a few different snapshot in the simulation as it goes. So you can see here this like hot bubble coming out of material. And this is later again in time where there was actually the bubble on both sides more explicitly. So you see there's a lot of this really hot gas. So this is reaching like 10 to the 7, 10 to the 8 degrees, this white color here. And you can see it going like crazy. And in fact, if you measure how much mass is going out in this gas, so the mass outflow rate, it's about the same as the star formation rate in the entire galaxy. So 20 to 30 solar masses per year of gas is turning into stars, but 20 to 30 solar masses per year is blown away in these winds. And the speed of these winds, they can reach 10,000 kilometers per second, which is the same as we saw in the quasars I showed you before. So you can have very fast winds. You can have quite a bit of outflow rate. However, check out this disk. It's surviving. It's not been destroyed at all. We still see this cold gas in the galaxy, and this gas is still happily forming stars. It's not being affected much, even though these outflows exist. So the black hole is creating these winds, and it's pushing material away, but the stars are just keep forming just fine. There's a small effect if you zoom in just around the black hole, but overall, in the whole scale of the galaxy, it's still just forming stars, and the disk is surviving. So then we pushed it one step further, as I mentioned before. So Orion Rose led this work where, with Cloudy, she ionized the gas in all possible directions with different luminosity of AGN. So what you have again here on the left-hand side is that same galaxy. It's a big disk seen edge on again. So this is a density map. So you can see, of course, that there's more denser where the disk is. And then these three panels on the right, there are three different AGN luminosity. So this is kind of like a bright Seyfert, so kind of moderate AGN luminosity, and then the brighter, and then the very bright quasar here on the right-hand side. So and these three panels on the top, they're showing the ionized fraction. So you can see that this galaxy is all neutral, and what we see is what we call ionization cones. So above and below the disk, there's these cones where the gas is ionized. And as we crank up the luminosity of the AGN, so it's brighter and brighter on the black hole, the cones are even more ionized, and they get even bigger, but still, the disk is surviving. You can see the black material here, so the gas remains neutral. At least it doesn't see any new ionization from the black hole, even in the most luminous case. And we now understand that this is due to the structure of the ISM of the galaxy, because we did not put a torus in here. We did not put this torus that would block certain direction. We actually tried to put the light in all directions around the black hole, but it still was blocked. So not by the torus, but by the galaxy itself. This is a zoom in, a very thin slice in the center of the galaxy, just around the center. Well, it's a few hundred parsec across. But what happens is you can see these denser clouds of material. So blue is denser here. And this is, again, these three panels correspond with here the most luminous AGN. And the only thing that's different is this little green material that's been ionized. So it basically is no longer forming stars. So this is actually this is a star formation rate map. So this material is gone, but this is already kind of not so dense compared to this. The dense clumps where most of the stars are forming, they're surviving fine, even fairly close in to the black hole. So the result from this work is that with the simulation of these isolated galaxies, we're able to generate these fast outflows or winds that we observe. And we can even have high outflow rates, at the order of the star formation rate. And if we add the photoionization even, so on top of the thermal feedback that makes the wind, we also photoionize with radiative transfer, there's still no immediate quenching, or there's no reduction of the star formation rate, nothing significant. At most, it was the order of 1 or 2%, even for the most luminous case. So this means that in terms of feedback, it seems that for an isolated disk galaxy, the black holes are not doing that much damage. One case I did not investigate, but which other people have studied, is a possible role of feedback from radio jet. This is a very interesting work I was not involved in it, but you can see here there's a galaxy which has a black hole in the middle, and then this is a cloud, a giant cloud of gas, which, like, why is it sitting there? It doesn't even have stars in it. Well, it turns out that if you look at this, well, this is the same image I was showing before, but if you look at larger distance, these two kind of magenta spots are radio lobes from a radio jet. So this giant, really long radio jet going away, and this is right in line with the radio jet. So it seems that the radio jet was able to push this big lump of gas outside of the galaxy. So this would seem to have maybe a more major impact, because this galaxy right now is not forming many stars. It looks pretty dead. But there's all this gas there. So they still hope that black holes can do something, but it would be that perhaps radio jets, in some cases, can expel material more readily than just the winds.
How do you know that it's not projection?
Well, so this might be projection in the sense that there's probably some angle with the radio jet already. But so if there's an angle in and out of the plane, we just have to assume that it would be in the right way. I don't know. Let's see to measure it. I guess if we can try to measure precisely the two redshift of these two things already to see if they're really in line. And I think they are, because this is H1, so you have to have the right frequency to detect the line. And then we know the redshift of this one. So at least these two are close enough. And I believe that this radio lobe is convincingly associated with this. But of course, what would be very nice is to have more cases, because one case is not going to allow us to conclude for sure. Although then saying it seems possible. OK, so the last few minutes, I just want to spend on showing you a very interesting case study of just a single galaxy where we can zoom in and revisit this question of the obscuration of the black hole, and also a case where we see clearly evidence of winds. So we don't know about feedback. So this is work with a recent instrument called MUSE, which is a multi-unit spectroscopic explorer, if I remember correctly. So this is what we call a 3D spectrograph on the VLT. So VLT is a very large telescope. It's a European telescope in Chile. So why do we say 3D spectroscopy? So instead of just taking one spectrum, so either by placing a slit or a hole on the galaxy and taking a spectrum by dispersing that light, this is like a diagram, but to illustrate that there's a spectrum taking on all these pixels. So in particular, this instrument can take 300 by 300 spectra. So it's like imagining like an image, but where each point is a spectrum. So that's 90,000 spectra. So it makes a data cube where you have your image, and the third dimension becomes the wavelength because it's a spectrum. So each pixel you have from blue to red light. So this is working in the optical. So this is great because with spectroscopy, we can say a lot about what's going on. We can say about the ionization, because with spectroscopy we can see emission lines if the gas is ionized. We can also look at different emission lines, so compare oxygen and hydrogen and see what's in the gas. But also we can do kinematics, which is very interesting, because emission lines are tracing the gas, so ionized gas. And if the gas is moving away from us or toward us, the lines are shifting red or blue corresponding to that. And also the stars, the spectra of stars has instead absorption lines, so we can distinguish the star spectrum from the gas spectrum. But similarly, for stars and for gas, the lines are also shifted blue or right depending on how the stars are moving compared to us. So we can compare if the stars are moving a certain way and the gas is moving the same way or not. So this is the galaxy NGC 7582. So it's a nearby galaxy. It's actually this one shown here. So it's shown on the side. This is a disk galaxy seen quite inclined. So it looks flattened because it's seen with an inclination. But it lives in a group. So these two galaxies are group members. And there's a tiny satellite also, galaxy here. And then on this map, so the background color image is what you would see in stars, although the colors are a bit coded here. They're a bit too blue. And the contours is gas, is neutral gas around galaxies. So what you can see is that the gas tend to extend farther than the stars. So we see the stars here making the galaxy, and then the gas goes further away. But it's this giant tail of gas coming out. And this we can now understand it, that there was a previous small galaxy that came in and joined the bigger galaxy, and it lost its gas on its way in. So we know it was so this is what we call a minor merger, because it's a minor galaxy compared to the bigger one, and the bigger galaxy is not too distorted. We know that it's not a tail because of this galaxy, because otherwise, with the dynamics, these guys would have a tail opposite for the interaction to make sense physically. So we have this interesting galaxy here that has a black hole, and the black hole is extremely obscured. We know that the little galaxy came in, but what else can we learn? So what we did is we used this MUSE instrument I was describing. So this is a MUSE field of view. So in this field of view, I have 300 by 300 spectra, so every little point. This is, again, the MUSE field of view with this red square. This is previous data from a different instrument, but that same idea. These are pixels with each having a spectrum. And this is color-coded by different emission lines that we see in the spectrum. So blue is a highly ionized oxygen. Well, it's twice ionized oxygen. Green is ionized nitrogen. And ionized hydrogen, H-alpha, is in red. So what you can see already, not super well, but I don't know if you can see from the back, but it seems to be this shape, like kind of a triangle, like a cone. Because the black hole lives here, and there's like this cone of highly ionized gas coming out. Now with the new instrument MUSE, it's on a bigger telescope, so we get more detail. So this is how we can now separate the different emission lines. And you can see even better this cone coming out of the center of the galaxy. And then you can see these blobs, which are just star-forming blobs in the disk. So there's this region of star formation in the disk of the galaxy. OK, fine. We can see where is the ionized gas. So this is gas ionized by stars, and the blue is gas ionized by the black hole. But what else can we say? So we see that there's some winds, it looks like, because it looks like it's coming out. But I'll show you how we can tell it's wind or not with the velocity maps. So this is now I'm going to show you the kinematics. So in the same field of view, this shows the kinematics of the stars. So this shows a rotational pattern, because what is blue is coming toward you, and what is red is coming away from you. So the whole disk is rotating like that, right? So this is what the stars are doing. So the stars in the galaxy are doing that. But interestingly, in the center, I don't know if you can see it, but it looks like it's either a ring or a smaller disk. It's rotating in the same direction, but faster. There's like a differential rotation there. What does this mean? It's not completely unusual, because other galaxies have this. It was not known before in this galaxy, but it happens before.
How do you get differential rotation?
Sorry. Just for the color is showing the velocity. So you can see that it goes back to being red, and then there's
a ruler right over there. It's not a yardstick.
Oh yeah. So if it's just a normal, if the disk is rotating like, let's say, a solid body, then it goes through like 0, the center of rotation. But this would just have a normal rotation curve where it would go down to 0 and then negative on the other side. But what it does instead is it goes down, up again to 0, very negative, less negative, and negative again. So it's this little region here where the contrast is higher. So the velocity is differential there. So this is very interesting, because the scale of this rotation corresponds to these dust lanes on about 600 parsec scale. So what's with 600 parsec scale? It's not at all the size of the torus. It's not that close to the black hole. But it's also nothing to do with the real scale of the galaxy. It's something in between. So that's already unusual. So what about the gas then? So the gas, it turns out that if we look at the emission lines and at the kinematics, there's actually two different components. There's one component of the gas. So if we look at the emission lines, that have a very similar pattern as the stars. So there's a very large-scale rotation. So again, blue toward you, red away from you. So there's a large-scale rotation. But then there's the second component of the gas, which is very strikingly the shape of a cone, like I was telling you before. But also there's a back cone, which we turn out that we're seeing behind the galaxy. So blue means toward us. So this is a cone that's not only ionized, but it's moving because it has a differential velocity. And the scale here saturates at about 300 kilometers per second. But I still have to measure it more closely. But I think it's going to reach maybe 400 or 500 kilometers per second. So you have to imagine that this little black hole that's tiny that we can't see is making this giant cone that's way not flowing toward us. And what is interesting is the cone base is pretty big. It seems like that it's not coming out of just a point like the black hole, but it's coming out of this 600 parsec scale, perhaps a ring that we saw before.
That's going away from us.
Blue is toward us, and red is away from us. So the away from us is behind the galaxy.
Oh, negative is towards us.
Yes.
Okay.
So
I'm sorry, is the red less because of obscuration? So you see less of the receding cone because of intervening dust?
yes.
Okay.
That's exactly right. And I'll show. Thanks, Greg.
Thank you.
I did not pay him for this. Okay. So finally, this is the last thing I'll show you about this galaxy. Is just to kind of wrap it up. So this is another image, actually from an amateur image of the galaxy. And this is the zone again that we see with MUSE instrument. So this is if I reconstruct a color image of the galaxy just for my cube. So I take 3 broad bands. And you can see it's very red here because it's very dusty. So it's very reddened. The light is reddened by the dust. And you can see also these large-scale dust lanes, which we could already see here. So now we recover these dust lanes. So what I'm going to show you next is a montage where I'll show you, so this is the starlight. And where it's dark, it's because there's dust and it's blocking the starlight. And if I add, I'm going to add in green the gas that's ionized by the AGN, and it looks like this. So let me go back and forth. So like I was saying before, we see a cone shape. And then this bright cone is in the front, and it's coming toward us, and it's in front of the disk of the galaxy. But then pay attention to the back cone. We can see it in between the dust lane. So we can see through the galaxy on the other side. And it's going away from us. So it's a case where we have symmetry cones with winds going like this, and there's a galaxy in between with some angle compared to us. So in addition to looking very nice, it's actually useful because we can learn about so the presence of winds, we can confirm it, fine. But I think the most interesting, this is just to show the 2 cones, the most interesting new thing is that it seems that this structure at 600 parsec is playing a bigger role than what we normally think about what's affecting black holes obscuration and black hole growth. And we think that the structure at 600 parsec, also because it has a differential rotation, it must have had some outside influence. And that's how, if you remember at the beginning, I showed you there was this tail of gas that we think comes from a smaller galaxy that went in. So the most likely scenario that we think, although we're not 100% sure, is that the small galaxy came in, perturbed the central part, or itself joined the central part, and made this intermediate scale structure, which is differentially rotating, but it's also collimating that cone, and it's probably obscuring the black hole. So what I just told you is basically put here. So this is a summary of the case study. Now we find this ionizing cone, and well, we find this kinematically distinct core. But I think that this new scenario of having a ring or disk from a minor merger is completely different from anything that people have thought about so far. Because people have been thinking either is a small torus introduced to you, or it's a large-scale galaxy, but like a global galaxy phenomenon, like a galaxy merger that would have enough gas to obscure the black hole. So this idea of having a minor merger being enough to obscure a black hole is interesting, because perhaps those minor mergers also play a role for growing black holes. And minor mergers are way more common than major mergers with two big galaxies coming together. So this is a very interesting and promising avenue to understand black hole growth and black hole obscuration. And now my final summary for the full talk. So I think we need really a multi-wavelength approach. I'll show you the importance of combining X-rays, infrared, optical, and radio, and everything we can to find the full picture between active black holes and galaxies and their connection. And it seems that the growth of black holes is the most closely related with the star formation rate of the host, which traces the total gas mass of the gas reservoir. And in terms of the feedback, it's easy to see these outflows or these winds. However, I would say that the impact on galaxies is still not established fully. And maybe the impact is quite often weak, or maybe it's delayed, that the impact would happen on a longer term that we haven't seen yet. And then the future is bright, of course, always is. And I think for this topic of supermassive black holes and galaxies, we're going to want to have the two very complementary approaches. One is to zoom in particular systems, like I showed you a case study. And then with the JWST, for example, which is going to be Hubble, the successor, we're going to have amazing detail in nearby galaxies. And then the other approach is statistical, including large data sets. And what I mean by large data sets is, for example, if you take DESI, LSST, or Euclid mission, we're going to get millions of spectra. So with millions, I think we can say something, hopefully. So I'll stop here. Thank you.
So we have plenty of time for questions. So let's start. John?
So what's the mass of the thing inside that little structure? You've got a distance, you've got a speed.
Ah, yeah, that little.
That little box up there.
I don't know. You mean like in stars?
Well, you know where it is, so you know how far apart they are. You know the speed, differential rotation of order.
Yeah, I didn't calculate it yet. Yeah, because I think we can get it. We can assume it's.
I don't know how far away it is, so I can't get it. But otherwise, it's all there.
What's the mass of the black hole from other measurements? Because people have measured it from.
In this galaxy, I don't think we have it. This is narrow. Not true. Okay, this is Seyfert-2 in the optical. It's Seyfert-1 in the infrared. But it's obscured not by a torus if it's Seyfert-1 in the infrared. And I think there might be broad Paschen alpha line. And I don't know what the number is. My guess?
What the radius of influence would be, and if the dynamics of that ring would be dominated by the dynamics by the gravitational field of the black hole or by the gravitational potential of the stars.
Yeah, I would guess it's a 10 to the 7 order. I think it's not very.
But from the bulge, from the end black hole sigma, you can estimate.
Yeah, all these great questions. I did not work out these numbers. I'm still writing the paper for this guy. But so those numbers should be in there. Yeah, so I'm not sure. That's a good point, though.
Oh, Ron?
You were looking at the unified model.
Yes.
And you were saying after you were showing us the simulation that you're not quite sure that the torus is left when you're doing that simulation. What do you think would survive from the unified model after this?
Yeah, so I think.
Could you repeat it? Because
Oh yeah.
Did you hear it? Because I couldn't.
Right. So there was so in a simulation that I showed, I mentioned that we're not implementing a torus in there. So there's not right now small-scale obscuration. And then the question was, what is left of the unified model if we still need it, despite the fact that we already see the cones, which is the galaxy, right? So I think we can learn something about the unified model in the sense that if these cones happen to be much too big with the galaxy collimation, it means that maybe it has to be collimated on smaller scale that we did not put in. So a constraint will come from comparing the opening angle of the cones in observed galaxies to the simulations. And if in observed galaxies the cone always seems with a smaller opening angle, it means that we must need a smaller scale collimation to do it.
Michael, Joe?
It's just a very silly question. On these active black holes, and there's this disk, or this accretion disk.
Yes.
Does the accretion disk tend to be oriented with respect to the galactic disk?
Right, so the question is if the black hole accretion disk is oriented along the same axis as the galactic disk, and no. So, however, I think what is not clear, there might be some mild alignment. I think it's clear that it's not a one-to-one alignment because we've seen, like, for example, radio jets at a different angle with respect to the disk. But there's also work that's found that it's not fully random, that there might be some very mild alignment. So if it's aligned, it would be subtle.
There's a fairly long history, 20, 30 years, interest in neutrino emission from AGNs and the possibility of observing those neutrinos. It's not happened yet. A lot of the early models were too, what would you say, optimistic, and were orders of magnitude larger than the limits put since then. Can you say anything about the state of modeling of the neutrino emission, whether there's any progress in understanding
So I don't.
why the early ones were so far off?
Okay, so the question is about neutrino emission from active galactic nuclei and if there are revised estimates of what we might expect, given that previous estimates were highly overestimated compared to what was observed. I don't work on this, but my understanding from talking with some colleagues at Saclay is it seems that even if you calculate that there should be some neutrino, even from the black hole from our own galaxy, the problem is that there's a lot of astrophysical sources also that could contaminate the signal, so you end up diluting and losing the signal, I think, compared to other sources. But since I don't work on this field exactly, I cannot say like details. But that's what I got just from talking with other colleagues who seem to work closer to that topic.
So I have a question. If you could go to to your MUSE data and show the velocity field of the cone for the gas. There, that's perfect. So it looks like the gas is kind of different kinematics from the stars because the gas really looks like a rotating disk all the way in, right? And then in the stars, you have these two knots. If you look at the stellar indices of those knots, do you see an age gradient? Do you see that it's something that the gas is getting down here and kind of jamming up in an inner radius and forming stars, and those are kind of formed in situ? Or is there estimates for like abundance gradients that would tell you that this was something that like the predecessor of a kinematically decoupled core or something that we see in early types later on?
Right, so I had a quick look. So the emission lines are much, much brighter here. So it washes out a bit of the absorption line signature. But if we still can try to subtract emission lines and see what's left, it's actually not that dissimilar. So what I did is I took a spectrum of just the little blue region and a spectrum of just the red region, and then I took some outside of on either side here, but outside of that core. And I did not do a full analysis of stellar age, but just comparing the spectra, they look quite similar. I was actually hoping for striking difference because it would have been a fun story.
If it comes from a satellite, then you'd expect there to be some differences.
Yeah.
Or are there indices you can use to measure chemical abundances of the material? Maybe purely stellar photospheric lines that don't get contaminated by emission lines, like Lick indices or something that you could use to try and measure the age gradients across there, like they do kind of for Sauron and Atlas 3D.
Maybe.
Okay.
So for emission lines, it's tricky because these are very much AGN dominated here.
Sure.
Around there.
But for the stellar.
And then for stellar lines, there could be a possibility. I have not done it yet just because there's so much in those MUSE data cubes.
It's crazily rich data, yeah, that's right.
When does one complain about having too much information,
yeah,
right?
It's like 90,000 spectra in one shot is kind of crazy. So any other questions? Alrighty, if not, let's thank Stephanie again.